So today we're going to look at another kind of wave. We've just talked about sound, and we looked at waves in a spring. We'll look at waves in other mediums as well, but today's wave is special. It's called an electromagnetic wave, and this is the kind of wave that includes light. So we talked about mechanical waves made by vibrating objects. Electromagnetic waves are going to be made by vibrating charge. Now, you may or may not know what a charge is, right? So we have our model of an atom. An atom has a nucleus, and in the nucleus you've got your protons, you've got your neutrons, and then flying all around outside are your electrons. Protons are positively charged, electrons are negatively charged, and mostly when electrons vibrate, they create these electromagnetic waves. So we don't need to vibrate the entire object, just a little charge inside in the matter that makes it up. Electromagnetic waves are also different from mechanical waves in that they don't need a medium. So we can see the stars, we can see the moon, even though between us and there is nothing but empty space. We can see the light. This is different from mechanical waves, which do require a medium. Electromagnetic waves can travel through empty space. Another thing that makes them different is how fast they go. Electromagnetic waves are really, really fast. They travel at the speed of light, which makes sense if light is an electromagnetic wave. So how fast is that? Well, the speed of light is so fast that it's given its own letter. We use the lowercase c to represent the speed of light in a vacuum. You might have seen the letter c in a very famous equation, E equals mc squared. C stands for the speed of light, and here's how big it is in our units. 3 times 10 to the 8th meters per second, which is a lot, right? And that's why I'm writing it in scientific notation, because otherwise I'd have to write a 3 with 8 zeros after it every time I wanted to work with this number. It's kind of hard to do, right? 1, 2, 3, 4, 5, 6, 7, 8. That's big, okay? It doesn't always travel at this speed. Just like other waves, the speed of a light wave or an electromagnetic wave does depend on the medium that it's traveling through. So this is the speed of light in a vacuum. We learned a bunch of equations for describing the motion of our waves. Distance equals speed times time. Speed equals wavelength times frequency. Frequency equals 1 over period. Period equals 1 over frequency. They're all still good equations. Only now what I'll put in for my speed will be that number 3 times 10 to the 8th if I'm working with light waves or any kind of electromagnetic wave. No difference. So let's see maybe how does this work in an actual problem. Here are 2 problems for you to try. This one is just in the old way, right? We have a distance and we have a speed. You're looking for time. And then we're going to repeat that problem. Instead of sound, we're going to do light. Let's check our work. So if we were doing sound, we would do distance equals speed times time. We would plug in our values and should get about 4.7 seconds. But if we're doing light, we're going to use the version distance equals speed times time with c in there. It is not necessary to write a c. You can keep that as v. You don't have to write it as the special symbol, but you do have to put in the number for the speed of light, 3 times 10 to the 8 or 3 with 8 zeros. And you get a very small number, so I've written that in scientific notation as well. This is microseconds, 5,000th of a second. Very, very fast. You may have heard the tale that when lightning strikes, if you count the number of seconds between the lightning and the thunder, you can tell how far away the lightning is. And you can. The light will reach you almost instantaneously, but it'll take about 5 seconds for every mile that it travels. Light waves are different in how they go through a medium from our mechanical waves. When light travels, it travels through the empty spaces briefly pausing to interact. So it kind of jumps from atom to atom as we think of this matter of glass. For example, these would be glass molecules, and light travels through this empty space to the first molecule, then it travels through empty space to the next molecule, and so on. Here's a little simulation to kind of think about what's going on here. So if we look in here, we have the light coming through the space, interacting with this model of an atom, being resent out, coming in, flying through that empty space, interacting, and moving on again. So what that means then is that the more interactions that the light has, the slower it will travel. And that has some implications for how light travels through a medium and what its speed will look like. Let's see if we can make predictions, right? Remember, the more empty space there is, the faster the light will go. The more molecules there are, the more densely packed, the slower it will go. So, should light be faster or slower in gas than a liquid? Light is going to be faster in a gas than a liquid than a solid because there's more empty space. Different frequencies of light might travel at different speeds. And this is because of the interactions with those molecules. It turns out that different frequencies have different amounts of interactions. Some frequencies don't interact at all, some interact a lot, and some might not get through at all. When a material does not let light through, when a material lets all the light through, we call it transparent, and when a material does not let light through, we call it opaque. We're going to watch this little video about what's called the electromagnetic spectrum. So we've been using the word light and electromagnetic wave kind of interchangeably, and we'll continue to do that. But there are lots of different kinds of electromagnetic wave. So as you watch this video, please record the different kinds of electromagnetic wave in order, and pay attention to which has the higher frequency and which has the longer wavelengths, and what we can talk about with the energy.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. In comparison to the football field-sized wavelengths of radio waves, gamma ray wavelengths are as small as atom nuclei.
Let's double check our list. We have our radio waves, microwaves, infrared radiation, visible light, ultraviolet light, X-rays, and gamma rays. Radio waves are the low frequency, long wavelength. Gamma rays are the high frequency and the short wavelength. So we're going in order from lowest to highest frequency, longest to shortest wavelength. And with light, the energy does depend on the amplitude, but it also depends on the frequency. Radio waves tend to be low energy waves, and gamma rays tend to be high energy waves. And that's why we think of gamma rays as being sort of dangerous, right? They cause the Hulk to form and things like that. Gamma rays can cause damage to your DNA, cause cancer, things like that. Radio waves really don't affect you much at all. Here's another image of the electromagnetic spectrum. You'll notice this middle part here, visible light. Visible light is itself a spectrum called the color spectrum, going from red up to violet. Infrared means right below red. Ultraviolet means right above violet. So this color spectrum fits right in there. We look at the world in visible light. The word visible means visible to human beings, but we have cameras that can take pictures in many different kinds of lights. So maybe you've seen the infrared goggles in TV or a movie, or maybe you've even tried them on. We can also take pictures of ultraviolet light. This is a flower taken with an ultraviolet filter. Some animals, like bees, can see ultraviolet. So finally, our color spectrum. You do need to know the color spectrum in order. Our color spectrum, sometimes people remember Roy G. Biv, red, orange, yellow, green, blue, indigo, violet.